RM, MRAM. So that first letter L, R, M stands for left, right, or midpoint or middle. And so I've seen these are like Riemann sums. There's a German mathematician, Riemann, let's see, I before E except for C. Okay, so Riemann sums. And so you could either have like a left rectangular area model, a right rectangular area model, a middle rectangular area model, or a trapezoid model. And so if this is like left rectangular approximation model, or area model, okay? So focus again is on the left. So if you have some kind of curve that you don't really know what exactly the antiderivative is, that you could construct a rectangle underneath it and construct like lots of rectangles underneath it, right? That's the whole idea. We're constructing rectangles. And the thing is that at some point you've got to decide, okay, now which side of the rectangle am I going to use for this area model? Well, if you choose the left side, right, then, you know, sometimes it might be over, sometimes it might be under, but at least you are consistent with how you're measuring it. So if you're choosing the left side of your rectangle, then that's called an LRAM, right? You're the left side of that particular division. Okay, RAM, right side. So for your RAM, it'd be a right rectangular approximation model. Or you could think of it as a Riemann sum, that's fine too. A right-sided rectangular area model. So now, when you are dealing, again, maybe you don't know what your curvature or what the function is, but if you start constructing rectangles underneath, so if you know like these are the intervals of your rectangle, when you construct your rectangle, you will go up till the right side hits the function and then come across. You go up to the right side, hits the function, and come across. Sometimes you might get an overestimate. Sometimes you might get an underestimate. So that's the whole point of an approximation. And then the thought behind this is that the skinnier these rectangles are, the less over and under space you would have, and therefore the closer and closer and closer you get for this area model. Now, tomorrow, we're going to look at, well, what if you could go so small, like infinitely small, that these rectangles are just heights? Could we then derive our integral formula? And that's exactly what we're going to do. Super excited for that. M for middle or midpoint. So again, so you are still going to use rectangles for MRAM. And if you have your function, whatever it looks like, and you know what your interval is, let's go, I guess, red, why not? So if this is your interval and this is your interval, you would construct it based on where the middle hits. So if the middle hits here, then you go on either side. So then you would find the area of that rectangle. And then the last one, trapezoid. So trapezoid sort of is like midpoint, except for you actually use both heights and then connect them. So our trapezoids, normally when we think trapezoids, you know, I think from geometry, we think about our trapezoids like this, right? Like our parallel bases are the top and the bottom. Take that trapezoid and turn it sideways, and you're going to start inscribing a whole bunch of trapezoids underneath your particular curve. So if this is my graph, again, just some arbitrary function, and I want to construct trapezoids, so let's say this is the interval and this is the interval, I would actually go up, touch the graph, go up, touch the graph, and then make a line. So again, this is parallel, my trapezoid is underneath. My trapezoid is sideways. And so the trapezoids, you know, you think about, like, again, the smaller the interval, the better those become, and basically becoming like linear approximations of each of those, you know, intervals. So like from here to here, you know, there's this trapezoid. From here to here, there's this trapezoid. Now, in terms of your width, like you could either have equal width as you partition this off, or you could have varied width, and it's going to tell you, you know, depending on the problem. Okay, so let's look at an example here of a function. I know how to find the area under this. I can do the antiderivative, but I'm going to use this as a model with some of these area models, just to kind of see, you know, like how would you convey your answer, or how does that apply? So it does say use equal width, and so I'm going from 0 to 16. Okay, Okay, so the first one says do RAM4. So again, this little subscript here tells you how many of those divisions. I want 4 subdivisions, equal length. So then I think about, okay, there's a distance of 16, divide by 4, I get each length to be 4. Now, eventually we're going to formalize that to this idea of b minus a over n, where b and a would be like the right endpoint, the left endpoint. So a span of 16 over 0, which is 16, divided by the number of rectangles, 4, which means that I want a width of every rectangle equal to 4. So I would go from 0 to 4, would be my first rectangle. I go from 4 to 8 would be my second one, 8 to 12, and 12 to 16. If I'm choosing the right side, then I'm going to pick, right? And then I'm going to pick the right side between 0 and 4 was 4. So I would go up, and there would be my first rectangle. So I'd want to find that area. And so, I'd figure out what that, what is that area? And then from 4 to 8, green, it's going to look like Christmas colors, up to there, and find the area of that rectangle. And then maybe go back to red, 8 to 12, find this area. And then our last one from 0 to 16, which is actually just flat, but still that's our rectangle. So I want to convey that, and so I want to show some work here, and really here's what I'll be looking for. So you have your width, and area of a rectangle is just base times height. So your very first rectangle, the base is 4, the height is whatever the right side is, which is f of 4. So I could say 4, oops, let's go a little bit thinner. There we go. 4 times f of 4 plus, let's do the next rectangle. This rectangle from 8 to 4 is still a width of 4. The right side is f of 8. 4 times f of 8 plus 4 times f of 12, which is the height of the third rectangle, plus 4 times f of 16. Now in this particular case, there's a 4 I could have actually factored out. If it's unequal width, then you can't do that. But I could factor out a 4 if I wanted to and figure out what is f of 4. I either can look at the actual picture, I could plug in 4 to the function. 4 squared is 16, negative 1/16 of 16 is negative 1, plus 16 is 15. So I know that f of 4 would be 15. And then if I evaluate 8, again, you could either look at the graph or you could substitute in the function. 8 squared is 64, negative 1/16 of 64 is negative 4, plus 16 is 12. Remember, I've already factored that 4 out. We could plug in 12 and then plug in 16 as well. 12 squared, which would be 144. 144 over 16, I don't know, what is that? 144 over 16, is that 8, I think? 8, I know, 6, whatever it is, I have a 272, oh, 9. Brain fart, sorry, long day. It's 9, so it's negative 9 plus 16, which is 7. We already factored the 4 out, and then f of 16, which was 0. So if I add all this up, or think about like 4 times 15, 4 times 12, 4 times 7, 4 times 0, that'll be the area of the 4 rectangles as an approximation. So 15 and 12 is 27, 27 and 7 is 34, so I have 4 times 34, which is equal to, I believe, 136 as an approximation. Okay? Now, that's definitely an under approximation because look at all the extra space. Okay, this was a very clunky, very cumbersome set of rectangles. It's not very good at all. So if we made them narrower, we would get better accuracy. But again, just for the sake of this, I don't want to do a whole bunch of rectangles here. I know that you know how to multiply. I'm just kind of showing you the different models. Okay? If I do an MRAM 8, that means I need 8 different rectangles. And so if I think about this b minus a over n, so 16 minus 0 is 16 divided by 8, means the width of every one is 2. So now, for this particular approximation, every 2, I'm going to draw a rectangle. And I'm going to be evaluating, so let's see, I don't know, let's go red, it's fine. So I'm going to be going from 0 and 2, 2 and 4, 4 and 6, 6 and 8, 8 and 10, 10 and 12, 12 and 14, 14 and 16. And I'm going to be evaluating the midpoint. So between 0 and 2, the value is 1. So I figure out 1, and I draw a rectangle for f of 1. And then between 2 and 4 is 3. So wherever that one goes, I draw that rectangle. So already I can tell it's a better approximation. At 5, and then at 7. Some of it's over, some of it's under, but it's clearly a better approximation. 11, 14, and then between those two is 15. And so, I would add up all of those areas in terms of rectangles. Again, just base times height, base times height, base times height. And just in terms of like the notation of our function, every rectangle is a base of 2, and then the height of the first one would have been f of 1 plus 2 times f of 3 plus 2 times f of 5 plus 2 times f of 7 plus 2 times f of 9. See, it's very tedious. Plus 2 times f of 11 plus 2 times f of 13 plus 2 times f of 15. And again, you could calculate those. I'm okay with just leaving it like this for now. Just again, demonstrating what MRAM might look like for this particular example. LRAM, same 8 rectangles that I have up here partitioned, right? 0 to 2, 2 to 4, 4 to 6, 6 to 8. But now I'm going to choose the left side. So that would be the first rectangle would be on the f of 0. The second rectangle's left boundary is 2, and then 4, and then 6, 8, 10, 12, 14 would be my last partition. So that would look something like, again, 2 times f of 0 plus 2 times f of 2 plus 2 times f of 4 plus 2 times f of 6 plus 2 times f of 8 plus 2 times f of 10 plus 2 times f of 12 plus 2 times f of 14, because we've picked the left side of that rectangle. Okay, the last one I want to do in this video, and then we'll go to the next video, trapezoid.